everyone. Thanks for sticking around. It's 4:30 or 1:30 my time a.m. So this is my first time at giving a talk at 1:30 a.m. Thank you again for staying awake. I promise you I'll buy you coffee right after if you stick around for the rest of the talk. So this is going to be a fairly classical game theory talk presentation, but with mainly focused application in manipulation domain. And this topic started long time ago when I was a student, when I was a postdoc, in fact. We asked a simple question, and that is how to do task and motion planning for manipulation, for manipulators. And that led to a very large project. So I started with working with Lydia Kavraki and Moshe Vardi, and they continue to collaborate on this project. And 2 PhD theses came out of it. So Kyung and Andrew already wrote their PhD thesis on this topic. And Karan Muvala, who's sitting right there, he's actually writing his thesis, well, not writing, developing his thesis, a couple of years early, on this topic. So really the whole thing started with the fact that we said, okay, robots are coming to our society. It was, again, some time ago, so it was at the beginning of the era. Robots are coming to our society, and the minimum thing that we can do is perform something for these robots that can perform task and motion in presence of human. So because as they are coming to our society, they are going to have to interact with us. So self-driving cars are a good example of it. We had enough talks about that today. Car factory, a lot of assembly line, robot, human interaction for increasing efficiency, surgical robots, home assistive robots. The market is going to be huge, or already is. There's a lot of economical incentives to do that. So when it comes to reality, we're still lacking behind. But my interest is not really in the failures of actuation or difficulties of maybe doing motion planning, but rather things that could go wrong in interactions and how robots should take on strategies to overcome complications that do not need to happen. Specifically, we are interested in enabling robots with complex tasks, the tasks already given, to efficiently and effectively interact with humans. And the setting that we have in mind is really factory settings, where you have an assembly line, and on one side you have a robot, on the other side you have a human, and they are supposed to be collaboratively working together to assemble, pieces together to develop some object. So here is an abstract scenario we have. We have a human here, we have a robot, and they're interacting through objects. One question is, well, can we learn the task from demonstrations? That's a project that I'm also interested in. And actually, we have Kandai, a student here, graduated a couple of days ago, in fact. He's going to present a paper on Thursday in collaboration with Georgios Finakis. He's going to talk about task and motion planning, learning tasks from demonstration, and planning for it for multi-agent systems. But that's not what we are talking about, what we are talking about today. We are talking about the fact that robot already has a task, but we don't know if the human is going to be a novice human in collaboration or an expert human going to be collaborating. So does the robot need to correct human mistakes? Does the robot need to just sit back and watch the human perform tasks? What does he have to do? So we are going to ask these questions. So here's a demo of what we are considering. So there are a bunch of objects. We have a robot. In this task, the robot already has to have a constructed arch with 2 white columns and a black piece on top. And the human keeps interrupting, and it goes on and on and on. So what should be the strategy of the robot to complete the task? So there are key questions that we need to answer. First question is how to model this interaction, what strategies guarantee task completion, how to ensure productive interactions, how to manage computational complexity. It's a huge space of planning. and what assumptions are appropriate for these interactions. Assumptions are important to provide guarantees. So what kind of assumptions do we need to provide? All right, I'm from a formal methods background, and like some of us here, Christy gave a talk this morning. So we are looking at this box, and we have formalized input, and we want formalized output with guarantees. The inputs we have to this box are task specification for the robot, the environment that the robot is going to be working in this case, it's going to be objects in a workspace, and they're going to be manipulatable. And robot model, like what's the degree of freedom of my robot, what joints can move. And as an output, I want a strategy that guarantees the completion of the task in face of interventions by other agents and humans. So starting from the top left, task specification, very quickly, task for me is a logical statement which does not have any ambiguity. It translates to a mathematical objective, mathematical object that can be easily incorporated into algorithms. Specifically, I'm looking at temporal logics. And it are a lot more strict and expressive than cost functions. And in fact, you can use cost functions in conjunction with these temporal formulas. So if I have a task that says, first collect all the dirty dishes, and then wash them, and eventually put them away, and do not put them away until they're dry, I can actually write that in a temporal logic, linear temporal logic formula that looks like this. It says collect, and next wash, and eventually put away, and not put away until dry. And the beauty of this is that it automatically translates. We have algorithms that translate this to an automaton, to a state machine that has specific states. We call them accepting states. Here is shown as double-edged circles. And if I start from initial state and make my way all the way to that special state, it means that I have accomplished my task. So one way to do this is to collect the dishes and wash, dry, and put them away all at the same time. I can notice that this is not physically possible, but logically it is possible because it's in a logical space. It has no knowledge of the physical space. But there is also another path. It says collect dishes, wash them, do not do anything while they're not dry, and then dry and put them away at the same time, then you're done. So we have a task representation that is really nice. Now looking at my other components, I already can get an automaton from my task. Now I need to somehow reason about my environment and my robot dynamics in conjunction with my automaton. So I need to have a representation of my environment and my robot in a way that I can use that in conjunction with my automaton. So looking at manipulation domain, I have this robotic arm. It's 7 degrees of freedom. It has, what are it, 1, 2, 3, 4, 5 objects. Each of them is their own configuration space. So I have a product space of gigantic degree of freedom space. And I want to reason about it using a very complex specification. It's going to be very difficult. It's a continuous space. And I'm going to have a hard time doing any computation. So instead, I'm going to do analysis. I'm going to realize that my objective is to manipulate objects. So I have a set of objects that I'm interested in. And my task requires me to only manipulate them with respect to some locations of interest. So I can reduce my space of reasoning to objects being in locations. And those locations of interest are shown here. And my objects can move in between locations of interest through an intermediate state. And that intermediate state is either the end effector of the robot or some other place on the table. So now that I have these two, now I can talk about the actions of the robot. How does the robot actually manipulate objects? Well, I can do an abstraction and say that I have special actions, like grasping an object. And then once my robot can grasp an object, it can transfer it to some location. And then you can release it at that location, and then transfer the end effector to somewhere else. So these are the sequence of actions I have. And therefore, I can have this action abstraction space where grasp and release are actually motion primitives. And transfer and transit are actions that I need to perform motion planning for. And that can be done online. So with this predefined space of reasoning, I can easily now turn this into a graph where I have the permutation of all the objects in locations and their manipulation and how it can be evolved over time. So this becomes a finite graph, gigantic, because essentially the number of locations to the power of number of objects is the size of the graph. And I can manipulate them this way. So my end effector can transition to get to an object, grasp it, and then release it and move on to other states. Great, so I have a finite abstraction of my continuous space. I'm going to also consider cost of actions to have these quantities on the edges. But the problem that I'm looking at is actually a interaction between a human and a robot. So how can I go from this space to this space of reasoning, and what happens to my graph up there? Well, I'm going to make a couple of assumptions. One is that the interaction between the robot and human is through the objects only. I'm not going to worry about safety because safety has to be taken care of by low-level controllers. You can use barrier functions, for instance, so the robot arm wouldn't run into the human arm. And secondly, the motions of the human actions are a lot faster than the robot. Using those two assumptions, then you can see that every time my robot is trying to transition to another location, the human can intervene and move an object. That means as I'm performing a transition, now human can perform an action in between the transitioning between objects. As my robot is trying to, let's say, the human intervenes, now the object has moved from that location to this location. Now my robot has to transition again to get to that location, but the human, again, can perform two actions, either intervene and move the object back, or let the robot grasp the object. So this is now a two-player game in discrete domain, but in continuous domain, it's actually a concurrent game, by the assumption that the human actions are a lot faster than robot actions. So we turn a concurrent continuous space game into a turn-based game, a finite turn-based game. So I have a well-defined turn-based game in discrete domain where I have a set of states for the robot, set of states for the human, and a set of actions and the corresponding costs for the robot. Now I'm going to just use this graph as a running example for the rest of the talk. I have system states or robot states as square, and circles are the environment states. And the robot can, at robot states, only the robot can take an action. At human states, only the human can take actions. And it moves on it goes on according to a strategy. The robot picks a strategy according to some a strategy that tells it whether to go right or left, and the human can go either left or right according to its own strategy. And once both players have chosen their strategies, then I'm going to have a cumulative cost. So now the question becomes, how am I going to compose these two to achieve the objective of the robot? And that is to complete the task. And this is a classical formalism question. So what we do is we have a cryptic structure representing our system. We have an automaton that represents our task. We compose them, and the composition, which is known as the product, is actually a structure that resembles my initial cryptic structure, but also captures the requirements of my task. So it inherits all the actions and costs from the game and all those special states that are accepting states from the automaton. So now the objective becomes to reach these special states, which means I'm going to achieve my task. I'm also going to inherit all the costs and actions from the game. So this is a bigger game where the objective is to reach those special states. So it's a reachability game, also known as DFA game. But as soon as I have fixed my strategy and the human actually has the strategy, I'm going to have a payoff function, which means the total cost of actually playing that game. And that in this case would be, let's say my robot takes action left, the human takes action right, the robot takes action left again, the cumulative cost is 7. So I have a cost corresponding to each pairs of state strategies. I can either assume the human is going to be cooperative, meaning that the objective of the human is to minimize my costs, and my objective is to minimize my own costs. So it would be a min-min game. Or I can assume that the human has adversarial strategy, which could be a min-max game. So now the question becomes, which one am I going to choose to compute a strategy? Well, I'm going to give you one more piece of information to make that choice easier. I'm going to say that the robot has some energy budget. I do not want it to spend more than certain budget to achieve the task. Then what kind of strategy should the robot take? Well, since we want guarantees and we want to make sure that it achieves the task and also remains below the budget, then it becomes a min-max game. It's an adversarial game. It naturally becomes that choice. So it's an adversarial game. Now I need to solve it very quickly. And luckily, we have algorithms that do that very quickly. And it's very simple. It's based on value iteration. You start by assigning 0 to the accepting states and a value of infinity to everything else. And then you start doing back propagation using value iteration. For the human states, for the system states, you choose min between the edges. So this would be 5. And then for the human states, you choose max. So in this case, it would be 5 here between 0 and 5. And then you do this back propagation all the way up. And now you have clearly, you know clearly from which states you can reach the accepting state. And those are the ones that have finite value. And those states that cannot guarantee getting to an accepting state, they have infinity value. And so that determines your winning strategy. You can always force a visit to an accepting state. And those states that have a value below your threshold, they can also guarantee that you will never spend more energy than you need to get to the accepting state. So very nice. This algorithm actually has polynomial complexity, and it results to very interesting interactions. So going back to that example of building an arch, so the robot is now putting the columns, and the human comes and puts a black box as a column. That's a mistake. The robot can recover from that and build the arch, hopefully very soon. Now the human comes and intervenes again, and he can always recover because he has a winning strategy. We already computed offline, and it's guaranteed to achieve it within the budget. And the last piece. Okay, so that's not only for arch building. Other examples include that, like I want to align all of the boxes in a diagonal line where with the black box pin in the middle, already top left object is in the right position. So now the robot to finish the task just needs to put it in the middle, and human comes and says, no, I want the other diagonal, but misses the final position or final location by mistake, and the robot just adapts to it and fixes it. Great. So it means that using games allows us to have a very good modeling of the interaction. The winning strategies are the ones that can provide guarantees. Now, the next question is, are these winning strategies sufficient to have productive interaction? Because you're interacting with humans. So to test that, we set up an experiment. We said, okay, we have a shared workspace. This is a shared station between a human and the robot. And we have a station only for the robot, where the human cannot intervene. I'm going to give low action cost to the robot to operate here, to incentivize the robot to operate in the shared workspace. And going to give a high cost for that environment. And I'm going to apply the framework I just explained. And here's what I get. It's building an arch, and it keeps building it in the same position, and that is in the robot workstation. It will never bother to seek collaboration with the human in the shared workstation. And that's because the robot is always looking for adversarial human, or assumes that human is adversarial. So if I want to very quickly explain that, is I have this game. I'm going to look at a tabular evaluation of it. So the robot has actions left and right. So it can take left or right. And the human can decide whether to intervene or not intervene. So if the robot takes action left and the human intervenes, the robot is going to endure a cost of 7. If the human doesn't intervene, the robot is going to endure a cost of 1. But if the robot chooses right, it's going to take cost of 5, and the human will not have any choices other than just 1. So in both cases, we will have 5. Between this column and that column, the robot will choose the right column where the maximum cost is lower. So it means that the robot will eliminate choices from human to make sure it's a well-controlled game. The robot always wins, which is not ideal because we are not really giving human options to cooperate with us. So the interaction is not really productive in this case. So we started looking around and said, what type of games can actually provide that collaboration with human that we care about? Well, it turns out regret games provide very interesting view for us. And that is regret providing a method of looking at the fact that in the hindsight, if I look back on my actions, would I regret them or not? And in mathematical formulation, essentially you say that if I pick an action right now, and I get some sort of a cost because of the human strategy, if I knew the human strategy, what would have been my optimal action? And the difference between the two values is my regret. So if I play that game, would that be cooperative? Would that help me to seek cooperation with the human? So very quickly, going back to that example again, and now let's evaluate the regret for that game. So the robot taking left action and a human intervening, it will give me a cost of 7. If I knew human was going to intervene, I would have taken action right. So I would have made a total of 5, a cost of 5. The difference is 2. So my regret value would be 2. Now, going left, and if I knew human was going to not intervene, my regret would have been 0. Same thing going right. If I knew the human was not going to intervene on this side, my cost 5 minus, I would have taken, intervene, sorry, it will intervene here. So it would be 5 minus 5 because my optimal choice would have been 5. And finally, in the last case, I would get a regret of 4. Now, looking at these two columns again, my maximum regret here is 4, there is 2, so I would pick that choice, which means I would actually go and seek cooperation with a human and allow a human a chance to actually cooperate with me. So it turns out regret games do provide the incentives for the robot to seek collaboration with humans. And we do have, luckily, algorithms that do it, that perform that computation for us. But they are pseudo-polynomial, and the degree of polynomial is at least 5, which means I can have a hard time computing these strategies. So I'm not going to go through the computation of the algorithm, but essentially there's an expansion of the tree of the game or unrolling of the game according to the budget that I have. I will have to unroll the game until I reach my maximum budget. And I have to construct 2 intermediate trees until I'll be able to compute the regret minimizing strategies. But once I have the regret minimizing strategies, I in fact can get very interesting results. So going back to that example, building an arch. So now I am seeing cooperation, but the human intervenes and being adversarial, and the robot retrieves and builds the arch on its own station. We looked at this from different examples. In the interest of time, I'm going to skip this example. But now regret games do provide good cooperation. However, one thing that they are lacking is that because the algorithms are expensive, you're going to need a lot of memory for these games. So if I say in the arch example, if I give a budget of 10, there are 2 million states that I need to deal with. The computation time is not too bad, but the amount of memory is about 6 gigabytes that these algorithms require to compute regret minimizing strategies. If I just increase the budget slightly, I more than double increase the number of states and double the memory usage to 12 gigabytes. If I slightly increase the budget more, I double the number of states again, and now I'm at 21 gigabytes of memory. So it's a very expensive algorithms. So the question becomes, is it computationally tractable? Well, it turns out we can use techniques that is already very well established in formal methods, and that is symbolic representation of our games. So we can actually use these games to be represented as Boolean variables for each state. That means that I'm going to have, for instance, if I choose 10 Boolean variables, I can represent 2 to the power of 10 states. And I get to use Boolean operators such as conjunction and disjunction and negation to perform algorithmic operators or algorithmic operations. So that will really reduce my computational complexity. So if I represent states using Boolean variables, represent actions using Boolean variables, and use smart data structure like BDDs to represent states and their corresponding edges. And now edges will be represented as sets of states to sets of states. So my algorithmic approach is going to be reasoning about sets of states at the same time rather than single state at a time. This is going to buy me a lot of computation power and memory. So looking at comparison with symbolic implementation versus the explicit implementation, you can see that the computation times are more than 2 orders of magnitude difference. And in terms of memory, I went from 21 gigabytes to 0.3 gigabytes. All right, so I'm going to skip this. Just one more thing. So now we are looking at what are the assumptions that we are actually looking at and how we can relax those assumptions. So going back to that example, we realized that one major assumption that we are making here is that we don't know anything about the human. No intention, we don't know anything about the past performances of the human. We don't know whether they're novice or expert. So can we utilize that information? Another one is that to avoid this case that the human can infinite number of times intervene and prevent you from achieving tasks, we always artificially put a large number as a maximum number of interventions that human can perform to be able to have winning strategies. So can we relax those assumptions? And it turns out going to stochastic games will allow you to use past informations as ways of keeping the human still strategic, choosing actions according to their objective without us knowing the objective, but at least having some incentives of the human has these intentions or has had those intentions in the past using probability distributions. So we can actually go from reactive synthesis, which assumes nothing about human, and probabilistic synthesis, which is just about policies without knowing and without giving strategies to the adversary. Now we can have stochastic games that combines the best of both worlds. But it will have some problems with computations, and Karan will be presenting a paper on that tomorrow morning in formal methods section. All right, so I'm gonna leave the interesting parts to him to describe tomorrow. I'm just gonna skip to the conclusion since everybody is waiting for me to finish. Okay, here you go. All right, so in conclusion, robotic manipulation is a very difficult problem. And especially when it comes into interaction with humans, not only because of safety, but also the type of strategies a robot should take. And games provide a very good framework of reasoning and modeling these interactions. But the type of games that you use is very important. Are you looking for cooperation? Are you looking for adversarial behaviors? Are you looking for some sort of a quantitative measure? If you do not have any data, in our experience, regret minimizing strategies or regret minimizing games are a very good representation and a very good way of providing guarantees and seeking cooperation at the same time. And along with those, symbolic representations of these games can help with computation. Stochastic games are rich, but very expensive. And this is just the beginning of the road for us to investigate further how we can mitigate these computational bottlenecks. And lastly, but not least, all of our tools are available through our websites, all on GitHub. So feel free to reach out and or download them or play them around. And Karan is actually giving a presentation on his tool on the last day of the conference. On that note, thank you. And I'll be happy to answer your questions, and I will buy you coffee.
Thank you, Morteza. That was very interesting. Can take a question.
Hi, Morteza. Thanks a lot, great work. The stochastic games, does that mean that you model a human as an MVP?
No, the human is strategic, but once an action of the human is chosen, then there is a probability distribution. And also, so there are multiple aspects that we can use stochastic part. Another aspect is when the robot is picking an action and performing an action, is there a chance that human will intervene? And if the human intervenes, then the human has a choice of an action. So it's always robot picking an action, human picking an action, and then there is a probability distribution. Mm-hmm.
My question is, when you are minimizing the regrets, so is an online repeating random setting or just a one-shot game?
Thanks for the question. Actually, regret has been used a lot in machine learning in an online manner. What we are doing here is all offline. So that's why it's a very expensive algorithm. It means that you have to unfold the game offline and look for that budget that you're looking at, and then play a game on that unfolded game. So that's why it's very expensive. It's offline. But once you compute that strategy, it's just a lookup table online.
But offline, I also need to like strategy human many times. Like human may have some strategy distribution, let's say, and then online there's no human strategy distribution.
So we account for all the human strategies offline. So that's why it's so expensive. If you have some information about what types of strategies humans are interested in and what type of distributions they're using, you can probably reduce it to an MDP, Markov decision process, or you can use stochastic games if there are still aspects that the human need to make decisions as a strategic agent.
I see.
Hi, thank you so much for your talk. I also have a question about the regret minimization section. I see why for the example you provided with those payoffs, regret minimization improved cooperation. But I'm struggling to see why that would be true in general. Can you provide some intuition?
So the intuition behind regret minimizing strategies is that, first of all, you're looking at winning strategies. And then among the winning strategies, the adversarial example always just picks the one that quickly finishes the game. Whereas in regret minimizing strategies, among the winning strategies, it's going to look at the one that perhaps can extend to the limit of your budget before it becomes conservative. So it seeks cooperation because there is a chance of saving costs if the human chooses to be cooperative. But if there is a way that the robot can violate the specification, the requirement, then it retrieves and then performs a task on its own. So as you increase the budget, you're essentially allowing the robot to ask for more cooperation from the human and giving more chances for cooperation. So that's the intuition.